In this lecture we will solve two questions. The first question, we find out the size of angle AMQ. This angle is equals to x. We have to find out the value of x, the value of angle x. The second question, we find out the area of this circle that is described by trapezoid ABCD. So let's start with the first question. In the drawing we have a semicircle. AB is the diameter of the semicircle. Point O is the center of the semicircle. We also know that line segment OS equals to line segment SB. And inside this semicircle we have this square PQSO. Again, our task is to find out the size of this angle AMQ. The size of this angle AMQ is equals to x. We have to find out the value of x. So first of all, we know that all the angles in any square are right angles. So those four angles are all right angles. This is a right angle. This is also a right angle. This is a right angle. In addition, we know that all the sides of any square are equal to each other. So in square PQSO, side OS is equal to side QS. Again, OS equals to QS. So OS equals to QS. But according to what is given in the question, OS also equals to SB. And for this equation, QS equals to SB, QS equals to OS equals to SB. We derive that QS equals to SB. So side QS equals to side SB. In the next step, we join points B and Q together by straight line. And we will extend the straight line BQ by a straight line until it touches the circle. We define the touching point of the extended line segment BQ with this circle. This point is point N. By doing this construction, we can do triangle QBS. This is triangle QBS. We know that AB is the diameter of this semicircle. So AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle. That is a right angle. Plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So triangle QSB is a right triangle, and we know that according to the rule that in front of equal sides in the triangle there are equal angles, we get that in the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the side of this angle as y, then the sides of this angle must be also equal to y because they are equal to each other, according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have the right angle Q as B? We have y plus y is 2y plus this angle that is the right angle. In total, the sum of those three angles must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So if we found out that in the right angle Q as B, the sum of its three angles must be equal to 180 degrees. 2y plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation, and you get that 2y equals to 180 degrees minus 90 degrees is 90 degrees. 2y equals to 90 degrees. Here we divide this equation by 2. And finally we get that the missing angle y equals to 90 degrees over 2, that is 45 degrees. Actually, this is the missing angle y that is equal to 45 degrees in its side. And this is also the angle y that is equal to 45 degrees in its side. We joined points B and Q by straight line, and then we extended the straight line BQ by straight line. When you extend the straight line by straight line, the result must be a straight line. Therefore, BN is also a straight line. BN is a straight line. So if we focus on the left side of the straight line BN at point Q, so here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have the left side of the straight line BN at point Q? We have this angle that is 45 degrees in its side, plus this is a right angle, plus this missing angle, that's actually angle PQN. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. And again, the sum of the angles on the left side of the straight line NB at point Q must be equal to 180 degrees. So 45 degrees plus 90 degrees plus the missing angle PQN, in total it must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees is 135 degrees, so we subtract 135 degrees from this equation. And you get that the missing angle PQN is equal to 180 degrees plus 135 degrees, 135 degrees, 90 degrees plus 45 degrees is 135 degrees. So we subtract 135 degrees from this equation and get that the missing angle PQN equals to 180 degrees minus 135 degrees equals to 45 degrees. So the missing angle PQN equals to 45 degrees in its size. This is the missing angle PQN that equals to 45 degrees in its size. In the next step, we will join points M and N together by straight line. And we'll also join points A and N together by side line. When joining points A and N, we created peripheral angle A and B. This is peripheral angle A and B. Peripheral angle A and B subtend on chord AB. That is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Repeat quickly rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle. And therefore, according to this rule, rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. One to another drawing, we have peripheral angle A and B, which is subtend on chord AB, that is the diameter of the semicircle. So write it down. This is the diameter of the semicircle. And therefore, according to rule 7, peripheral angle A and B must be equal to 90 degrees in its size. So angle A and B, peripheral angle A and B equals to 90 degrees in its size. This is angle AMN. And again, this is angle AMN. Angle AMN subtend on chord AN. Again, angle AMN or peripheral angle AMN subtend on chord AN. Likewise, we have angle ABN. This is angle ABN that subtend on the same chord, chord AN. So those two peripheral angles are both subtend on the same chord, chord AN, and therefore they must be equal to each other in their sizes, according to rule 16. So repeat quickly rule 16. According to rule 16, peripheral angles that subtend on the same chord are equal to each other. In the drawing we have a circle. This is peripheral angle AOB that subtend on chord AB. Likewise, this is peripheral angle ACB that subtend on the same chord, chord AB. And because of the fact that those two peripheral angles subtend on the same chord, chord AB, they must be equal to each other in their sizes. That is to say, peripheral angle AOB equals to peripheral angle ACB, or alpha equals to beta. So, if two peripheral angles subtend, if two or more peripheral angles subtend on the same chord, then they must be equal to each other in their sizes. So we can implement rule 16 in our drawing. When I put in our drawing, we have this is peripheral angle AMN. Peripheral angle AMN subtend on chord AN. Likewise, this is peripheral angle ABN. Peripheral angle ABN subtend on the same chord, chord AN, and therefore those two peripheral angles that subtend on the same chord, chord AB must be equal to each other in their sizes. But peripheral angle ABN equals to 45 degrees in size, and therefore peripheral angle AMN that subtend on the same chord, chord AN must be also equal to 45 degrees in size, according to rule 16, of course. In the next step, we will focus on the big right triangle, triangle A and B. This is the big right triangle, triangle A and B. In the big right triangle, triangle A and B, this angle equals to 45 degrees in size. This is a right angle. Therefore, this missing angle must be also equal to 45 degrees in size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. So this missing angle, angle NAB, equals to 45 degrees in size. We have the rule that says that in front of equal angles in the triangle, they are equal size. Repeat again. in front of equal angles in the triangle, there are equal sides. So in the big right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. That is to say, side AN equals to side BN. AN equals to BN. And because of the fact that in the right triangle A and B, side AN equals to side NB, the right triangle A and B is an isosceles triangle. So, as you know, the right triangle A and B is also an isosceles triangle. Triangle A and B is an isosceles triangle. And the base of this isosceles triangle, triangle A and B, is AB. Again, AB is the base of the isosceles triangle, triangle A and B. But AB is also the diameter. So as you know, AB is the diameter, and AB is the base of the isosceles triangle, triangle A and B. AB is the base. So AB is simultaneously the diameter of the semicircle and is also the base of this triangle, triangle A and B. So here we can implement rule 24 in the isosceles triangle, triangle A and B. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. So in the drawing, we have the isosceles triangle, triangle ABC. That is to say, side AB equals to side AC, the whole triangle ABC is an isosceles triangle. The base of this triangle ABC is BC. The perpendicular to the base from point A, the perpendicular to the base BC, first of all, because of the fact that AO is the perpendicular to the base, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular ON, the perpendicular AO, this is the perpendicular AO, bisects the base BC. Again, the perpendicular AO bisects the base BC. This is to say, it divides the base BC into two halves. Each half equals to BC over 2. So the first half BO is BC over 2, and the second half OC is also BC over 2. So BO equals to OC equals to BC over 2. So we can implement rule 24 in our drawing. Why? Because in our drawing we have the isosceles triangle, triangle A and B. And according to rule 24, the perpendicular from point N to the base AB bisect the base AB. But AB is also the diameter of the semicircle. So if the radius of this semicircle equals to R, then the diameter must be equal to 2R. So the diameter AB is also the base AB is equals to 2R. So the perpendicular from point N to the base AB bisects the base AB. So each half must be equal to AB over 2. AB over 2 is 2R over 2 because AB equals to 2R. 2R over 2 is R. So the first half is R, and the second half is also R. It is actually the radius of this semicircle. The perpendicular to the base AB bisects the base AB. If the perpendicular to the base bisects the base AB, it means that the perpendicular to the base touches the base AB at its midpoint. What is the midpoint of AB? AB is also the diameter. And we know that the diameter of the semicircle, we know that the diameter the midpoint of the diameter of any circle or semicircle is its center of the semicircle or circle. So the midpoint of the diameter AB is at point O, that is the center of the circle. Okay, again, the diameter, the midpoint of the diameter AB is at the center of this semicircle, that is point O. So the perpendicular from point A, N, we touch the base AB at point O, because it bisects the base AB. And the midpoint of AB is at point O, that is the center of the center of the semicircle. So the perpendicular from point N, we touch the diameter AB at point O. So first of all, NO is a perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. The perpendicular NO bisects the base AB. The first half AO is the radius, because AB over 2 is 2R over 2. So the first half AO is the radius of this semicircle, and the second half OB is also the radius of this semicircle. So here we have in square PQSO, the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. And we have the rule that in front, that the corresponding angles between parallel lines are equal to each other. And again, corresponding angles between parallel lines are equal to each other. In the drawing we have line 1 that is parallel to line 2. Line 3 cuts the two parallel lines at those 2 points. And according to this rule, those angles are defined as corresponding angles, and they are located between the parallel lines line 1 and line 2. We know that line 1 is parallel to line 2. So those two corresponding angles that are located between the parallel lines 1 and 2 must be equal to each other in their sizes. That is to say, line 1 equals to line 2. So you can implement this rule in our drawing. Why? Because in our drawing we have those two corresponding angles that are located between the parallel lines PQ and OS. PQ is parallel to OS because the opposite sides of a square are parallel to each other. So those two corresponding angles that are located between the parallel lines PQ and OS must be also equal to each other in their sizes. That is to say, those two angles are equal to each other. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees in its size. In the next step, I prove that quadrilateral MNQP, this quadrilateral MNQP is a cyclic quadrilateral. What is a cyclic quadrilateral? A cyclic quadrilateral is a quadrilateral that can be blocked by a circle. That is to say, all of its 4 vertices will touch the circle. So we prove that quadrilateral MNQP can be blocked by a circle. So first of all, we know that any triangle can be blocked by a circle. So this is a triangle NQP that we can block triangle NQP by a circle. And this is also angle NQP that is equal to 45 degrees in its size. So copy this triangle to a new page. This is angle NQP, it is also triangle NQP. According to the rule that all triangles are cyclic, it means that we can block this triangle NQP by a circle. So I block this triangle NQP by this circle. And we know that angle NQP equals to 45 degrees in size. So the three vertices N, Q, and P, they all touches the circle. The question is if the four vertex P of quadrilateral NMQP will also touch the circle. If we prove that point P, that is the vertex, also touches the circle or is on the circle, it means that quadrilateral PQ and P is a cyclic quadrilateral. So here we have this is triangle NQP. This is blocked by circle because you know that any triangle is a cyclic triangle. It can be blocked by circle. So if we rotate this angle NQP around this circle, and we will not change the size of this angle NQP, and the axis is NP, we create infinite triangles that each of them is equal to 45 degrees inside. Why? Because we rotate angle NQP without changing the size of it, that is 45 degrees. In this way, we created infinite triangles that each of them is equal to 45 degrees in size. One of the triangles that will be created, one of the angles that will be created will be angle PMN, that is also equal to 45 degrees in its size. This is angle PMN, that is also equal to 45 degrees in its size. Okay, one out of the infinite angles that will be created by rotating angle PQN around this circle will be this angle PMN, that is also equal to 45 degrees in its size. In the next step, we join points M and Q together by straight line. By joining points M and Q, we get the quadrilateral NMQP. In this way, we will prove that quadrilateral NMQP is a cyclic quadrilateral, that is to say, it can be blocked by circle. You can see that all of its four vertices, that is to say N, M, Q, and P, touches this circle, and therefore quadrilateral NMQP is a cyclic quadrilateral. So we can block this quadrilateral NMQP by circle. Actually, you can ask also, how do you know that angle PMN is equal to 45 degrees in its size and it's subset on NP? How do you know that it touches the circle at point M? Maybe it is outside this circle. Actually, angle PMN cannot be outside this circle. Why? Because if angle PMN is outside this circle, it must touch chord PN. And if angle PMN is outside this circle, it will be less than 45 degrees. So it is impossible that angle PMN is outside this circle. But you can also ask why angle PMN is at this circle. Maybe it is inside the circle. Maybe angle PMN is located here inside the circle. It is impossible that angle PMN will be located here. Why? Because here angle PMN will be greater than 45 degrees. So outside the circle it will be less than 45 degrees, and inside the circle it will be greater than 45 degrees. In order that angle PMN will be equal to 45 degrees and also will subtend on PN, it must touch the circle at any point. Okay, so therefore angle PMN is also it is located on the circle, not inside the circle or not outside the circle. So this is angle PMN that touches the circle at point M, and this way created quadrilateral PQMN, This is a cyclic quadrilateral because all of its four vertices N, M, Q, O, P touches the circle. So if you wonder that this is quadrilateral P, Q, M, N. This is a cyclic quadrilateral. So we can, that is to say, we can block this quadrilateral P, Q, M, N by a circle. So I block this quadrilateral by a circle, P, Q, M, N. The red circle blocks this quadrilateral P, Q, M, N. Why? Because all the four vertices of quadrilateral P, Q, M, N touches the circle, the red circle, at different points. This is point N, this is on the red circle, this is point M, this is point Q, and this is point P. So quadrilateral P, M, Q, N is described by this red circle. So here we can implement a rule that states that the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. Repeat again, the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. So we can implement the rule in our drawing, because in our drawing we have quadrilateral MNQP, that is a cyclic quadrilateral, as you can see. So in quadrilateral NMQP, the sum of those two opposite angles must be equal to 180 degrees according to the rule that I read. So this is angle NPQ, that is a right angle. So angle NPQ plus the opposite angle, is actually angle NMQ. In total, the sum of those two opposite angles must be equal to 180 degrees according to the rule that I read to you. The sum of those two opposite angles must be equal to 180 degrees. This is angle NPQ, that is a right angle, that is to say it is equal to 90 degrees in size. Plus this is angle NMQ. Angle NMQ in total close to 45 degrees plus X. And it is equal to 180 degrees. Repeat again. In total, we should find out that $90 degrees plus 45 degrees plus X equals to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, so we subtract 135 degrees from the equation. And we get that the missing angle X, that is the angle that we are looking for in this question, it is equal to 180 degrees minus 135 degrees is 45 degrees. So actually, this is the missing angle X, this is also equal to angle AMQ. This is angle AMQ, this is equal to X. So angle AMQ is equal to X is equal to 45 degrees in size. And that is the answer to the first question. Repeat again, we found out that this is angle AMQ is equal to X is equal to 45 degrees in size. So we finish with the first question. In the next step, I will present to you the second question, and we solve the second question of this lecture. Our task in the second question is to find out the area of this circle that is inscribed by this trapezoid ABCD. Okay, again, our task is to find out the area of this circle that is inscribed by trapezoid ABCD, or trapezoid ABCD blocks this circle. So in the drawing we have trapezoid ABCD. Those two angles are both right angles. Side AB of trapezoid ABCD equals to 3 units now. We also know that the area of this trapezoid ABCD is equal to 3 square units in its side. Again, the area of trapezoid ABCD is equal to 3 square units in its side. Again, our task is to find out the area of this circle that is inscribed by this trapezoid ABCD. So, first of all, we define the relevant points to this question with letters. We define the point of tendency of tangent DC with this circle. This point is point E. We define the point of tendency of tangent AD with this circle. This point is point F. And finally, we define the point of tendency of tangent AB with this circle. This point is point G. In the next step, we will define the center of this circle. This point is point O. And we will define the radius of this circle as X. And we will join points O and G together by straight line. Point O is the center of this circle. Point G is the point on the circle itself. Therefore, OG is the radius of this circle. This equals to X according to our definition. So actually here we can implement rule 1 in our drawing. In pinch rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle. This is tangent AB, that is tangent to this circle at point M. In addition, we have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule 1. So we can actually implement rule 1 in our drawing. How because in our drawing, we have the radius OA, the radius OG that is equals to X. The radius OG is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever your radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees. According to rule 1, of course. So in the next step, I'll implement rule 1 in our drawing without any explanation. In the next step, we'll join points O and F together by straight line. OF is of course the radius of this circle, is equals to X. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So, in quadrangle FOGA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this four-piece triangle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this four-piece triangle must be equal to 90 degrees in its size. So in quadrilateral FOGA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a tesseract angle if not a square. So we need to quadrilateral FOGA is a right angle because it has 4 right angles. But we also know that opposite sides of a right angle are equal to each other. So right angle FOGA, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA is also must be equal to x. Actually, this quadrilateral is not a rectangle but a square. But we can relate to this quadrilateral as a rectangle. Likewise, we join points O and D together by a straight line. OE is of course the radius of this circle, equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DEFO we have 1, 2, 3 right angles. And therefore this four-piece angle must be equal to 90 degrees inside, according to the order the sum of the angles in any quadrilateral equals to 360 degrees. So in quadrilateral DEOF we have 4 right angles, and therefore can relate to quadrilateral DEOF as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOF, side OE must be equal to the opposite side OF. Side OE must be equal to the opposite side DF. But OE is x, therefore the opposite side DF must be also equal to x units in its length. So side DA in total equals to x plus x, that is 2x. DA is definitely a straight line. Why DA is a straight line? Because DA is one side of this trapezoid ABCD. Actually, before I continue, I'll explain what is a trapezoid. A trapezoid is a quadrilateral with one pair of parallel sides. Again, a trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. In trapezoid ABCD, if we define the two parallel sides, those two parallel sides are defined as the bases of trapezoid ABCD. So if we define the base DC as A and the base AB as B, that is to say the base AB equals to B units in its length according to our definition, then the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees to two parallel bases. Repeat again, a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case it is A plus B times the height edge over 2. In the next step, we will define the length of side DC as A. I already proved in the previous lecture that DA plus CB equals to DC plus AB. Again, DA plus CB equals to DC plus AB according to all 2. So I will not repeat on the same proof again. So we know that DA plus CB equals to DC plus AB. So write it down. DA plus the opposite side CB equals to DC plus AB. Repeat again. In the previous lecture, we already proved that DA plus CB equals to DC plus AB. This is actually according to rule 2. The lengths of two tangents from a common standpoint to a circle are equal. DA is A. According to our definition, DA equals to A. Plus AB. AB equals to 3 units in its length, according to what is given as the question. Actually, it is DA, that is A, plus AB. DA is 2x. Please again, made a mistake. DA is not A, but DA equals to 2x according to what we already found out. So DA is 2x plus CB. CB is the missing side, so we leave it as it is. And it is equals to DC. DC equals to A units in its length, according to our definition. Plus AB. AB equals to 3 units in its length, according to what is given as the question. So in total, we actually found out that (2x) plus the missing side CB equals to A plus 3. Here we'll subtract 2x from this equation, and we get that the missing side CB equals to A plus 3 minus 2x units in its length. So we found out that this is the missing side CB, is equals to A plus 3 minus 2x units in its length. In the next step, we will do a construction, that is to say, from point C, we will do perpendicular on AB. Again, from point C, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we're going to do the big quadrilateral DCMA. Inside the big quadrilateral DCMA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DCMA, we have 4 angles, and according to rule 5, we can remember to quadrilateral DCMA as a rectangle because it has 4 rectangles. So I write it down. The big quadrilateral DCM is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side AM. But DC is A, therefore the opposite side AM must be also equal to A units in its length. Likewise, according to the sum rule, in the same big rectangle DCAM, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the length of this missing line segment? Line segment MB. From the drawing, it is very easy to see that MB equals to AB minus AM. So if you know, the missing line segment MB equals to AB minus AM. So MB equals to AB. AB is 3 according to what is given in the question. Minus AM. AM is A. So in total, we should find out that the missing side line segment MB is equal to 3 minus A units in its length. MB equals to 3 minus A units in its length. In the next step, I'll copy the right triangle CMB in a new page, and we will implement on this right triangle the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I copy this right triangle CMB in a new page, and we will implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. The hypotenuse CB equals to A plus 3 minus 2x units in its length. Side CM equals to 2x and side MB equals to 3 minus A. Actually, this is the right triangle CMB, this is the coverage from the original drawing. In this right triangle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So, let it know. CB squared, this is the square of the hypotenuse, equals to CM squared plus MB squared. CB equals to A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared. And is equals to CM squared. CM is 2x, therefore CM squared is 2x squared, that is 4x squared. Plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus 8 squared. So now we found out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus 8 squared. We will open the brackets on both sides of this equation according to the algebraic identity that states that A minus B squared equals to A squared plus B squared plus 2 times A times B. So according to the algebraic identity that I mentioned, a plus 3 minus 2x squared must be equal to a plus 3 squared plus 2x squared, that is 4x squared, plus 2 times a plus 3 times 2x. And it is equals to 4x squared plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared minus 2 times 3 times 8, that is minus 6a. We'll open the brackets of this expression and we get that a plus 3 squared equals to a squared plus 3 squared, that is 9, plus 2 times a times 3, that is 6a, plus 4x squared minus 2 times a plus 3 times 2x equals to 4x squared plus 9 plus a squared minus 6a. So we have here a squared plus 9 plus 6a plus 4x squared minus 2 times 2x is minus 4x. So in total this expression equals to minus 4x times a plus 3, and it is equals to 4x squared plus 9 here we have plus a squared minus 6a. So this is the expression that we got after we open the brackets on both sides of the equation. So here we have a squared on both sides of this equation, so a squared gets cancelled. And we also have 9 on both sides of the equation, so 9 also gets cancelled. And we have 4x squared on both sides of this equation, so 4x squared will also get cancelled. So we cancel all those two expressions. This side of the equation we left only with 6a minus 4x times a plus 3, while on the other side of the equation we left only with minus 6a. So in total, if you found out that 6a minus 4x times a plus 3 equals to minus 6a. So here we will add 6a and also minus 4x times a plus 3 to this equation simultaneously, and we get that 6a plus 6a is 12a. This equals to 4x times a plus 3. So 12a equals to 4x times a plus 3. Here we divide this equation by 4. And we get that 2a over 4 is 3a. So 3a equals to 4x over 4 is x. So in total we have here with x times a plus 3. And again, if we found out that 3a equals to x times a plus 3. Here we divide this equation by a plus 3. And we get that x equals to 3a over a plus 3. Repeat again, if you found out that in total x, that is the radius of this circle, is equals to 3a over a plus 3. In the next step, we find out the area of this big trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. So the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say DC plus AB, times the height is CM because it's made with the two parallel bases, but it's CM, the height CM over 2. Repeat again, the area of this trapezoid ABCD in total is equal to the sum of the two parallel bases, that is to say DC plus AB, times the height CM over 2. DC equals to A plus AB. AB equals to 3 units in this length, we only told us given us the question, times the height CM. CM equals to 2x divided by 2. So in total, we found out that the area of the trapezoid ABCD equals to a plus 3 times 2x over 2. We have 2 in the numerator and 2 in the numerator, so 2 gets cancelled. So in total, we found out that the area of trapezoid ABCD is equal to a plus 3 times x. But it is given as a question that the area of trapezoid ABCD equals to 3 square units in its length. So we can substitute the area of trapezoid ABCD in this equation by 3. So 3 equals to a plus 3 over x. Again, in total, we found out that 3 equals to a plus 3 times x. But we have only found out that x equals to 3a over a plus 3, so we can substitute x in this equation by 3a over a plus 3. So we'll do it now, and we get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. So in total, we found out that 3 equals to a plus 3 times 3a over a plus 3. We have 3 a plus 3 in the numerator, a plus 3 in the denominator, so a plus 3 gets cancelled. And we left only with 3 equals to 3a. 3 equals to 3a. Here we divide this equation by 3 and finally get that a equals to 3 over 3 is 1. So a equals to 1 unit in its length. So we can substitute x. We only found out that x equals to 3a over a plus 3. So we can substitute a in this equation by 1. We found out that x equals to 3a over a plus 3. So substitute a in this equation by 1, and we get that x equals to 3a. A is 1, so 3a is 3 times 1, that is 3, or a plus 3. So a is 1, so a plus 3 is 1 plus 3, that is 4. So in total, we have to find out that x, that is the radius of this circle, is equal to 3/4 units in its length. Our test is to find out the area of this circle. So if you know that the area of any circle is equal to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, if you found out the area of our circle must be equal to pi x squared. But x is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, if you found out that the area of our circle equals to either 9 pi over 16 square units in size, in terms of numbers, the area of this circle is equal to 1.767 square units in size. And again, if you found out that the area of this circle equals to either 9 pi over 16 square units in size, in terms of numbers, the area of this circle equals to 1.767 square units in size. So we finish with the first question. In the next step, I'm starting the lecture. We'll start with the first question, of course. Our task in the first question is to find out the size of this angle AMQ. This is equals to x. We have to find out the value of this angle x. So in the drawing we have a semicircle. AB is the diameter of the semicircle, point O is the center of this semicircle. Inside this semicircle we have this square PQSO. And we also know that OS equals to SB. Again, our test is to find out the size of this angle AMQ, this is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the square are right angles. So those angles are all right angles. AB is the diameter of this semicircle, so AB is the diameter, it is absolute straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to all three. All three says that the sum of the angles on one side of the straight line is equal to 180 degrees. So each angle we have at the upper side of the straight line AB at point S, we have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in size. So, we know that OS equals to SB in square PQSO. We know that all the sides are equal to each other. That is to say, side OS equals to side SO. So OS equals to SO, but it is given in the question that SB equals to SO. And from this equation, QS equals to OS equals to SB. we write that QS equals to SB. Again, QS equals to SB. So those two sides are equal to each other. So in the right small triangle QSB, in front of those two equal sides, we have those two areas that must be also equal to each other. Again, in their sizes. Again, in front of those two equal sides, we have those two areas that must be also equal to each other in their sizes. So if you define the size of this angle as y, then the size of this angle must be also equal to y according to the rule that I mentioned. And we know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have the right angle QSV? This is angle y plus angle y, that is 2y plus 90 degrees. In total, it must be equal to 180 degrees. And again, this right angle QSB, according to the Balanos one, 2y plus the right angle, in total, it must be equal to 180 degrees. Here, sometimes 90 degrees from the equation, if we found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divided the equation by 2, if we found out that y equals to 90 degrees over 2 is 45 degrees. So this is the missing again y that equals to 45 degrees in size, and this is also the missing again y that is also equals to 45 degrees in size. Actually, we joined points B and Q together by straight line, and then we extended the straight line BQ by straight line until it touches the circle. We define the starting point of the extended isolated BQ with the circle. This point is point N. When you extend the straight line by straight line, the result Bn must be also a straight line. So if you focus on the left side of the straight line Bn is point Q, here the sum of the areas must be equal to 180 degrees according to all three. So which areas we have the left side of the straight line Bn is point Q, we have 45 degrees plus 9 degrees plus the size of this missing again LQP, so that must be equal to 180 degrees according to all three. So again, in the left side of the straight line AB is point Q, the sum of the areas must be equal to 180 degrees according to all three. Therefore, which areas we have at the left side of the straight line AB is point Q, we have 45 degrees plus 9 degrees plus the size of the missing area PQN, in total must be equal to 180 degrees according to all three. So here we subtracted 45 degrees plus 90 degrees is 135 degrees. So we subtracted 135 degrees from this equation, and we found out that the missing area PQN equals to 180 degrees minus 135 degrees is 45 degrees. Okay, this is the missing area PQN is equals to 45 degrees in size. In the next step, we join points M and N together by straight line, and we join points N and A together by straight line. By joining points N and A, we get the triangle A and B. And triangle A and we get it here angle A and B. Peripheral A and B. Peripheral A and B subtend on AB, that is the diameter of this semicircle, and according to Rule 7, any peripheral that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, peripheral angle A and B must be equal to 90 degrees in its size. So in the right diagonal A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, in the right triangle A and B, in front of those two angles, we have those two sides that must be also equal to each other and their lengths. That is to say, side A equals to side BN. And therefore, triangle A and B is an associated triangle because those two sides are equal to each other. And triangle, the big right triangle A and B is also an associated triangle. So here we have those two peripheral angles. This is peripheral angle AMN, the subset on called AN. Likewise, We have another triangle. This is angle ABN that's subtend on the same chord called AN. And because of the fact that those two triangles are both subtend on the same chord called AN, they must be equal to each other on their sides. But triangle ABN is 45 degrees, therefore triangle AMN must be also equal to 45 degrees in its size. So here we can implement rule 24 in our drawing. According to rule 24, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. Triangle A and B is an associated triangle. According to rule 24, the perpendicular from point N to the base AB bisect the base AB. That is to say, it divides the base AB into two parts. Each part must be equal to AB over 2. But AB is also the diameter. The base of the right triangle A and B, and the right and associated triangle A and B is also the diameter of this circle. So if you define the radius of this circle as R, then the diameter must be equal to 2R. So AB equals to 2R. So each half must be equal to AB over 2. AB over 2 is 2R over 2, this is R. So the first half AO must be equal to R, and the second half OB must be also equal to R. And the diameter from point N to the base AB bisect the base AB. That is to say, the perpendicular from point N must touch the diameter AB at its midpoint. And you know that the perpendicular, the midpoint of any diameter is the center of the semicircle or a circle. So the midpoint of the diameter AB must be point O, that is the center of this semicircle, according to what is the answer question. Point O is the center of the circle. So the perpendicular from point N to the base AB will touch the base AB at point O, that is the center of the semicircle. So the perpendicular from point N, because NO is the perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. You know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. And we have the rule that corresponding angles between parallel lines are equal to each other. Those two angles are defined as corresponding angles, and they are located between the parallel lines PQ and OS. And therefore those two angles must be equal to each other. But this is the right angle, therefore this angle must be also equal to 90 degrees in its size. In the next step, I proved that quadrilateral MNQP is a cyclic quadrilateral. That is to say, you can block this quadrilateral by a circle. So, first of all, you know that any triangle can be blocked by a circle. So I copied this triangle MPQ to a new page, and we block this triangle MPQ in the circle. We know that angle MPQ equals to 45 degrees in size. So actually, this is triangle NPQ that can be blocked by a circle, and this is angle NQP that equals to 45 degrees in size from the original drawing. From the original drawing. So we can block this triangle NQP by a circle, and in the next step I rotated this angle PQN that is equals to 45 degrees in its size around this circle without changing the size of this circle, and the axis is PN. So the axis will not move, and I just rotated this angle NQP is equal to 45 degrees in size without changing the size of this angle. By doing this operation, you actually can do infinite triangles that each of them is equal to 45 degrees in its size. So one of the angles will be angle PMN. So this is angle PMN. This is angle PMN. This is equal to 45 degrees in its size. So this is angle PMN that was created by rotating angle NQP around this circle without changing the size of angle PQN. Is equals to 45 degrees in its size. So we can do angle PMN. This is also equals to 45 degrees in its size. Angle MPN is subtend on the same chord called NP. In the next step, we join points M and Q together. We join points M and Q together by straight line. So here we created quadrilateral NMQP that is described by this circle. So in this way, we should prove that quadrilateral NQP is a cyclic quadrilateral because we can block this quadrilateral by a circle. So actually blocked this quadrilateral MNQP by this red circle. The meaning of to block a quadrilateral by a circle, it means that all of its 4 vertices must lie on the circle. You can see that vertex N, vertex M, vertex Q and vertex P, they all lie on this red circle. So we should block this quadrilateral NMQP by this red circle. So here we can use the rule that any quadrilateral that can be blocked by a circle, that is to say any cyclic quadrilateral, the sum of its 2 opposite angles must be equal to 180 degrees. Again, any cyclic quadrilateral, the sum of its 2 opposite angles must be equal to 180 degrees. So that is to say those 2 angles, those 2 opposite angles in quadrilateral NMQP must be equal to 180 degrees in total. So this is angle NMQ plus angle NPQ. In total, the sum of those 2 angles must be equal to 180 degrees. Then again, in quadrilateral NMQP, angle NPQ plus the opposite angle NMB, total must be equal to 180 degrees. Angle NPQ is right angle, and this is again NMQ, that in total equals to 45 degrees plus x. And again, angle NPQ is right angle, plus angle NMQ, that equals to 45 degrees plus x, equals to 180 degrees. So in total, if you all know that 90 degrees plus 45 degrees plus x equals to 180 degrees. 90 degrees plus 45 degrees is 125 degrees. So if subtract 125 degrees from this equation, if I found out that the missing angle x, this is the missing angle x, that is also equal to angle AMQ, is equal to 180 degrees. Once 125 degrees is 45 degrees. So the missing angle AMQ, that is equal to x, is equal to 45 degrees in its size. So we finish with the first question. In the next step, I presented to you the second question. And solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by this trapezoid ABCD. So, in the drawing, we have trapezoid ABCD that blocks this circle. Of this circle is described by trapezoid ABCD. Those 2 angles, number 5 angles, and you also know that this is side AB of trapezoid ABCD, is equals to 3 units in its length, and the area of this trapezoid ABCD equals to 3 square units in its size. Again, our task is to find out the area of this circle that is described by this trapezoid ABCD. But first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of equal sides. This is quadrilateral ABCD. Side DC is parallel to the opposite side AB. Therefore, quadrilateral ABCD is defined as a trapezoid. The two parallel bases, the two parallel sides, that is to say DC and AB, are defined as the bases of this trapezoid ABCD. So the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say A plus B. So if we define the base DC as A and the base AB is B, then the area of this trapezoid ABCD in total must be equal to the sum of its two parallel bases, that is to say A plus B times the height edge over 2. The height edge must be 90 degrees with the two parallel bases. So repeat again, a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. That's, in this case it is A plus B times the height edge over 2. So in the first step, we define the relevant point to this question. We define the relevant point to this question with letters. We define the point of tendency of the DC. With this second, this point is point E. We define the point of tendency of the DA. With this second, this point is point F. And we define the point of tendency of tangent AB. With this second, this point is point G. And in the next step, we already proved that DA plus CB equals to DC plus AB. We already proved that DA plus CB equals to DC plus AB. But before that, we define the center of this circle. This point is point O. We define the radius of this circle as x. We join points O and G together by straight line. OG is the radius of the circle. This is equals to x. The radius of OG is equals to x is drawn to point G, that is the point of tendency of tangent AB with this circle. And now your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, the joint points O and F together by straight line. OF is the radius of this angle according to our definition, so according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, the joint points O and D together by straight line. O is the radius of this angle that is equal to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DOF, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees inside. Therefore, quadrilateral DEOF is the right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So right angle EDFO, side EO equals to the opposite side DE. But EO is x, therefore the opposite side DF must be also equal to x units in its name. Likewise, in the lower quadrilateral FOGA, we have 1, 2, 3 angles, and therefore this fourth angle must be also equal to 90 degrees inside. And therefore quadrilateral FOGA is the right angle, but we also know that the opposite sides of right angle are equal to each other. So in right angle FOGA, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA must be also equal to x units in its name. So in total, if we found out that DA equals to x plus x, this is 2x. We define the area of DC as A, and AB equals to 3 units in itself, according to what is given in the question. So repeat again, we already found out that we already proved that DA plus CB equals to DC plus AB. DA plus CB equals to DC plus AB. DA is 2x plus CB is the missing side, so it is, and it is equals to DC is A, plus AB is 3. So if you handle the 2x plus CB equals to A plus 3. Here we subtract 2x from the equation. If I handle the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side CB. This is equals to A plus 3 minus 2x units in its length. In the next step we did the construction, that is to say from point C we do perpendicular on AB. So this area equals to 90 degrees and this area also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. When we do this construction, we can detect parallel DC AB. Inside parallel DC AB we have 1, 2, 3 angles. Therefore this surface area must be also equal to 90 degrees inside. Therefore parallel DCMA is left angle. But we know that the opposite sides of right angle are equal to each other. So now that DCMA side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x in its length. Likewise, according to the same rule, the side of the DCMA side DC is equal to the opposite side AM. But DC is A, therefore the opposite side AM must be also equal to A. What is the length of this line segment MB? MB equals to AB minus AM. AB equals to AB minus AM. So MB equals to AB, this is 3 minus MB, this is A. So total MB equals to 3 minus A in its length. The next step I complete the right triangle CMB in a new page and we implement the Pythagoras theorem on this right triangle CMB. According to the Pythagoras theorem, in any right triangle, the square of the opposite equals to the sum of the squares of the perpendiculars. Okay, this is right triangle CMB, this is according to the original drawing. This right triangle CMB, according to the Pythagoras theorem, CB square equals to CM square plus MB square. CB is A plus 3 minus 2x, therefore CB square is A plus 3 minus 2x square, and it is equals to CM square. CM is 2x, therefore CM square is 4x square plus MB square. MB is 3 minus A, therefore MB square is 3 minus A square. So total if you handle that A plus 3 minus 2x square equals to 4x square plus 3 minus A square. We open the brackets on both sides of this equation. According to the algebraic identity, that A minus B square equals to A square plus B square minus 2 times A times B. So A plus 3 minus 2x square equals to A plus 3 square plus 2x square, that is 4x square, minus 2 times A plus 3 times 2x. And it is equals to 4x square plus 3 minus A square. 3 minus A square equals to 3 square, that is 9 plus A square, minus 2 times 3 times A, that is minus 6A. We open the brackets of this expression. If you follow that A plus 3 square equals to A square plus 3 square plus 2 times A times B. This is 2 times A times 3, that is plus 6A plus 4x square, and it is equals to minus 2 times A plus 3 times 2x. And it is equals to 4x square plus 9 plus A square minus 6A. We open the brackets of A plus 3 square, A plus 3 square equals to A square plus 3 square, that is 9 plus 2 times A times 3, that is 6A plus 4x square minus 2 times A plus 3 times x, and it is equals to 4x square plus 9 plus A square minus 6A. So here we have A square on both sides of the equation, so A square will get cancelled, and we have 9 on both sides of the equation, so 9 also get cancelled, and we have 4x square on both sides of the equation, so 4x will get cancelled. After I cancel all those two expressions, this side of the equation we have to only if 6A minus 4x times A plus 3, and the other side of the equation we have to only with 1 6A. In the next step we added 6A and also 4x plus A plus 3 and 4x times a plus 3 simultaneously of this equation. If I found out that 6a plus 6a is 12a equals to 4x times a plus 3. Here we divided this equation by 4. If I found out that 12a over 4 is 3a, so 3a equals to 4x over 4 is x times a plus 3. So here we divided the equation by a plus 3 and finally found out that x equals to 3a over a plus 3. In the next step, calculated the area of this trapezoid ABCD according to the formula that I presented to you at the beginning of the lecture. The area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB, times the height CM over 2. And again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually DC plus AB, times the height CM. CM is the height because it is the integration of the two parallel bases, so it is times the height CM over 2. DC is A, AB is 3, CM is 2x, divided by 2. We have 2 numerator and 2, the numerator, so 2 we can cancel. So in total, we found out that the area of trapezoid ABCD equals to a plus 3 times x. But it is given as the equation that the area of trapezoid ABCD equals to 3 square units inside, so we can substitute the area of trapezoid ABCD by 3, and it is equals to a plus 3 times x. We have already found out that x equals to 3a or a plus 3. So we substitute x here by 3a over a plus 3. 3 equals to a plus 3 and x equals to 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so it will be cancelled and we have to leave 3 equals to 3a. Here we divided the equation by 3 and found out that a equals to 1 unit in its length. We have the equation that says that x equals to 3a or a plus 3, so we can substitute a in this equation by 1 and we did it, and we found out that x equals to 3a is 3 times 1, that is 3, over a plus 3. A plus 3 is 1, so a plus 3 is 1 plus 3, that is 4. So in total, we actually found out that x, that is the radius of this circle, equals to 3/4 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared is 16. So in total, if we found out that the area that we are looking for in this equation, it is the area of this circle equals to either 9 pi over 16 square units in size, or terms of numbers, the area of this circle is equal to 1.767 square units in size. Okay, thank you very much.